Yes.
That's fine. I'll do the introductions to me if you don't mind. Pozdravljeni vsi skupaj, tudi tisti, ki ste sceni povezani z Zoom. Torej, danes imamo danes imamo ponovno večerjo na observatoriju. Danes bo predaval Martis, ki je postdoktorski sodelavec na fakulteti za matematiko in fiziko in se predvsem ukvarja z skopom, pa oziroma deluje v skopu. Načeloma prihaja iz Amerike, nekaj časa je pa deloval tudi v Kanadi. Danes bo predaval v angleščini. Potem vprašanja bojo tudi lahko potem boste postavili v slovenščini, bom jaz prevajal. Mogoče bo njih celo kaj razumel, tudi v slovenščini, pa bomo videli. Enako velja seveda tudi za poslušalcem Zoomom. Danes vreme na žalost ni najbolj ugodno, če pa se slučajno v teh 45 minutah sprosti vreme, bomo pa mogoče probali nekaj. Okay, Nick, what is yours, so please.
All right, thank you, Samo. And thank you to all of you for joining us here tonight. Right, so today we're going to talk about cosmic dust and how that fits into the general picture of astronomy. So both what it is, what we can learn about it, and what we can learn from it. So like Samo said, I'll take kind of general questions at the end, but also as I'm going through the presentation, if there's something that you're not understanding, you need clarification on something, you can feel free to stop me. And I want to keep everyone on the same page. We can go through together. And so, right, so we can all learn something. Right, so when we're talking about space and things that are very far away, things that are distant, it can be hard to wrap your mind around it. I thought we'd just start by pointing out that we are what I'm going to be talking about tonight, right? So, and actually, funnily enough, they knew this way back thousands of years ago, that dust thou art, and unto dust thou shalt return. So we are stardust, or if you prefer a more modern reference, according to Carl Sagan, the cosmos is also within us. So we're made of stardust. We're a way for the cosmos to know itself. So everything that I talk about today, the way that elements form, they come together, the way that stars evolve and eventually form planets that life can evolve on, it's all linked up together with what we're going to be talking about tonight. So these are some kind of the more spectacular images of what we'll be talking about tonight. And so when we are talking about dust, we're talking about these clouds or nebula that look like these giant kind of plumes of dust or clouds of smoke. And so kind of the goal by the end of the talk today is that you'll be able to look at something like this and not just appreciate it for, I think, the beauty that it has, but you'll be able to look at this picture and actually be able to see what an astronomer sees when they look at this picture, that it's not just pretty, but we can actually learn something by looking at these images about how the universe works. So to give just kind of a brief overview of what I want to talk about, we'll start with what dust is in terms of space dust. So what's it made of? Where does it come from? And why is it important in astronomy? And we'll see it is important for kind of a wide range of topics in astronomy. And then maybe at the end, I'm hoping to have enough time to touch a little bit on my own research, which is studying dust in very distant galaxies. So when we talk about cosmic dust, we're talking about kind of very small, solid particles that are hanging around in space. And so they range in size from a nanometer to about a micrometer. And so that's, if you take a meter and divide it up into around 1 million or 1 billion tiny pieces, that's the size of one of these particles, so very tiny. And so the larger ones are actually comparable in size to smoke particles. And that's actually a better analogy in your head for when we're talking about dust in space. It's kind of more similar to a smoke than, say, like the dust under your sofa at home. And then again, just to point out, this is small, so it's about, even the largest dust particles are 50 to 100 times smaller than the thickness of one of your hairs. And then kind of one more quick definition to get out of the way. Please. I'll be talking about what astronomers call metals a lot during this talk. So I'm sure most of you have seen a periodic table, but this is a little too complicated for us. For astronomers, almost the entire universe is made up of hydrogen and helium, so we'll use those ones by name. But anything heavier than that, we just call metal. So that'll be our distinction for the evening. So I will talk about the other elements more specifically, but I'm going to use kind of this terminology throughout the talk. So if I'm talking about metals, I just mean not hydrogen or helium. And so when we talk about the composition of dust, they're made of metals. And then broadly, there's kind of two chemical groups of dust. One is made primarily of hydrocarbons. So when you have carbon and hydrogen and oxygen molecules bonded together. And then roughly there's another type based on silicate molecules. So where the base is silicon and oxygen bounded together. And then you can get more complicated molecules from that. And then on the right here is actually a piece of dust that was captured in the upper parts of Earth's atmosphere and brought down and put under an electron microscope. And you see it's kind of this just clumpy little thing that actually, yeah, if you blew it up, maybe it would look like a little bit like the dust you're familiar with. So given that these things are so small, even if we take a nice big powerful telescope, pointed up at the sky, we're not going to see these tiny little things. So we have to see them indirectly. And one of the ways we can do that is by looking at how they affect light. So both the light that they give off by themselves and how they affect the light around them. So as astronomers, what we primarily use to study the universe is light. And so that's everything from radio waves and microwaves and infrared, or which you might kind of commonly be referred to as heat, right? If you look through heat goggles, you're seeing infrared light. And then the visible light that we see every day, what's coming out of these bulbs, is just a tiny fraction of that spectrum. And then the other part that will be relevant to the talk is that I'll be talking about red and blue. So by red, I'll just be talking about light that has longer wavelengths in general. So where the wavelength is the distance between these peaks on the wave, right? You see on the left, we have bigger wavelengths. And then as you move toward more blue, which I'll also call ultraviolet, more blue than, say, visible light, you have shorter wavelengths. Is that all good? Good, okay. Right, so now if we want to look at some of the light produced by dust, in this particular image, that's what we're seeing here in the green. So we see the points and the orange dots, those are stars. And then this kind of diffuse halo around it is dust that's been heated enough to give off its own light. And so that's one way that we're able to observe it. Good. So now, as we have a kind of a rough idea of what we're looking at, I want to talk a bit about how dust is formed in space. So there's kind of two main production channels that I want to talk about. The first is in supernovae, or stellar explosions. And then the other way is in the atmospheres or shells of old stars. But before we even get to that, we need, right, these metals that make up the dust, right? We need a way to turn all that hydrogen and helium in the universe into other elements. And all of that happens in stars. So in a star like our sun, the inside of it gets very, very hot, very, very dense, and so dense, in fact, that the atoms inside it, when they collide with each other, they actually confuse together. And so that's the process of nuclear fusion, where you take smaller elements, you smash them together, and then they build up into more complicated elements. So on the top here, that's an example. You don't need to worry about kind of all the steps, but just the general idea is that you can start with hydrogen atoms, smash them together, and you get helium. And then from there, you can keep on smashing them together and work all the way up through the periodic table, getting the rest of the elements. And then the one other thing to notice is that you can see in this diagram that different layers of the star are responsible for fusion of different elements. So based on the temperature in each of these layers, fusion results in the creation of different elements. Good, but this process can only get you so far. So you can see that even in the center of this star, we get to iron, but there are elements heavier than iron, right? So where do the rest of the elements come from? They come from a process called a supernova. And this is a really energetic event where a star explodes. So because it's relevant to kind of dust production, I'm going to briefly talk about the two different general types of supernovae. So on the left here is what's called a core collapse supernova. So this is what happens when you have a very massive star. And after it goes through the process of fusion, and so it combines all of its hydrogen into helium and helium into heavier elements, it runs out of fuel, basically. And once that fuel is gone, the star can no longer support itself. So it collapses down, and in that collapse, it kind of rebounds and explodes. And it becomes very, very bright. So on the left, you can see kind of an image on the sky, and that arrow pointing to that star. That's the star just burning normally on its own. And then on the right, that's when the supernova goes out. So you can see how much dramatically brighter it gets. And when it explodes, it spreads all of those elements into the area around it, spreading it to the regions around other stars. So the other type is what's called a type 1a supernova. And that happens when a type of star called a white dwarf is able to kind of eat more gas from a neighboring star. So you can see kind of in the diagram here, lots of stars actually exist in pairs. And so if you have one white dwarf and another star, it can start to suck some of the gas off of the atmosphere of its partner. But if it gets too greedy, it keeps on doing that. It'll overload and explode. And this kind of has the same effect, where you're spreading these elements into the surrounding area. And the type of supernova on the left, the core collapse, also produces a lot of carbon, so related to that first kind of type of dust I talked about. And the second type produces more silicon molecules, so it's more responsible for creating those silicate dust molecules. And just as an aside, I think that supernova remnants are some of the coolest looking things in astronomy. So they emit all across the entire electromagnetic spectrum. And so when you kind of put all of that light together into one image, you get some of these really, I think, beautiful, colorful images. So I thought I'd just share that. Good. Then the other way that I mentioned that dust can be made is in the atmospheres of old stars. And so that's what we're seeing here. So this type of star is called a red giant. It's a star that's kind of near the end of its life. And around the star, you can see kind of these rings or shells. And so if you remember back to that slide, we were talking about nuclear fusion. We saw the shells forming different elements in different layers of the star. So in this stage of a star's life, those outer shells get blown away. And so it spreads those elements into the surrounding area. And then those can be picked up to become part of dust molecules. And now we can be, a little bit more serious and look at our periodic table. And we can try to see where different elements primarily come from, right? So in black, you can see the hydrogen and helium and lithium. Most of it comes just from the beginning of the universe. It's produced in the Big Bang. But then you can see the different elements are produced in different amounts, right, from these dying stars, these red giants, from supernovae, and from some other sources. Good. And then when you take all of this together, there's kind of a recycling process of metals in the interstellar medium. So this space that all the stars exist in. So you start with kind of newborn stars. They undergo kind of their normal life. They fuse elements together. A star like the sun will become a red giant and spread the elements that it's made around. A heavier star will become, will undergo a supernova or to spread them around. And those elements are spread back around into the surrounding area, where they might find themselves into another star-forming nebula to be used in the next round of star formation, which is actually exactly what we'll talk about next. So the role that dust plays in allowing new stars to be formed. And so this is one kind of really spectacular image from the James Webb telescope, which I'm going to talk a bit more about later. But here you can see around these bright blue stars, which are kind of young, newly formed stars, we can see that there's lots of this gas and dust around them. And so why is that? Well, so in order to form a star, you need to take a cloud of gas, so the hydrogen and helium that makes up most of the star, but it starts off in just a big kind of diffuse, lumpy cloud. You need to get it to crunch down thousands and thousands of times into a tiny dot, and only then does it get hot enough to ignite fusion and become a star. And so if you start with kind of a diffuse cloud up in the top left here, and then eventually you can start to form little clumps, and those clumps keep on condensing, and then those clumps will start to spin, make disks, and eventually you'll get down to something that makes a star. But in order for it to condense that much, the gas needs to cool. So the hot gas it wants to bounce around quickly. It doesn't want to sink down into one place. And so that's where our dust plays a role. So when you have dust mixed around with the gas in these big clouds, you can have collisions between the gas particles and the dust particles. And when those collisions happen, heat or energy from the gas can get transferred to the dust. And the metal and the dust is much better at sending its energy away. So the kind of two diagrams here are two examples of how the metal molecules can send their energy away, either by undergoing atomic transitions or by making these kind of shaking motions. So I said that this is an example with a carbon dioxide molecule where you have a carbon and two oxygens, and you can see that there's these kind of wiggles or shaking that the molecule undergoes. And as it does this, it's able to send away energy. So it can absorb heat during collisions with the gas. And then as it absorbs heat from the gas can cool and eventually form down into stars. And so this will try to now give you a bit of a more visual of how that happens. So the time at the top, so this is in units of millions of years, but you can see we started, maybe I'm gonna actually try to start this over. So we start with just this big fluffy ball of gas, right? And then as it's able to cool, it starts to form these filaments. It gets more dense. And then eventually, you can see these bright spots. You can start to form stars where the gas condenses the most and gets cooled down the most. And then when the stars start to shine, they start to heat up the gas around them again with the energy that they put back in. And so you get kind of a feedback process where the gas is able to cool, stars form, but then the stars heat it up again. It has to cool again, right? So there's an ongoing cycle of star formation. Good. Then, okay, how are we doing so far? Following along? Any questions so far? No, I'm throwing a lot of information at you, but there's a lot I want to talk about. So, okay, so the next part we're going to talk about is how dust plays a role in planet formation. So just a couple slides ago, I showed here how the dust and the gas, when it condenses to form the new stars, when it gets down to the smallest levels and you get stars, the gas and dust will form kind of these disks around the star. And so this is what it actually looks like. So this image is created by kind of looking at a new young star, kind of blocking the star itself, because since it's so comparatively bright, and then to look at the disk around it. And this disk is primarily made of dust. And so I said that these dust particles are very tiny, but as they're spinning around, that's actually the material that planets are made from. And so I have another short video to play. But this is not a simulation. It's just kind of an artist's idea of how this happens. But you see there's the spinning disk of dust around the star. And you can see that there's these rings that start to be formed. And those rings are formed when the dust can start to clump together into bigger and bigger pieces, eventually go from a little dust molecule up into a pebble to a rock, then to something like an asteroid. And then they'll keep on gradually pulling themselves together with gravity over millions and millions of years until you get really, really big rocks, one of which we live on. Until it's they've kind of cleared the rest of these this dust disk away, and then you're left with a solar system. And so now we've talked about kind of things that dust does directly. So ways that we can study the dust in order to see how it behaves on its own. So now for kind of the rest of the talk, I want to talk about the other side. So how dust affects light, if you're interested in studying something else. So I think maybe most people have seen the type of phenomenon pictured here, where if you have, say, smoke or dust in the air and you shine a light, you can see the light beams when it passes through the smoke, right? And the fact that you can see the light hitting the smoke here, it means that some of the light is getting blocked by that smoke. And so we want to study what happens when that light gets blocked. So if we imagine you're an astronomer and there's some star that you are interested in studying, but there's a big dust cloud in between you. So the star is emitting light across the electromagnetic spectrum. For now, let's talk about just red and blue light, like we talked about at the beginning, right? So when it hits this dust cloud, the blue light is more likely to be absorbed. So the shorter wavelengths means that it interacts with the small dust particles more easily. And so the blue light gets absorbed. And also, some of that blue light gets what we call scattered. That just means it bounces off the dust and gets sent in another direction. And then some part of the rest of it is able to travel through the dust cloud. But the red light doesn't interact with the dust as strongly. So all of the red light gets through. And so now when you're looking at the star, you see a bunch of red light and not so much blue. So compared to what the star is giving off, the light will look more red. And so now I'm going to show just one of a couple of the real scientific graphs in the talk, where now we can actually measure how much light gets blocked as a function of the wavelength, right? So this is showing how much light gets blocked in, say, the infrared. It's not very much. In visible or optical light, more gets blocked. And in the ultraviolet, really a lot gets blocked. And these different curves are just showing how that happens in different galaxies. So the differing amount in different galaxies actually depends on the properties of the dust that we were talking about. So how big the grain sizes are and what the composition is. So if you have the carbon versus the silicon, it affects this relationship. And then just to kind of give some visuals for what that looks like, this is one particularly dense nearby dust cloud. And the white is showing the visible light. So when you're looking in just visible light, what's behind the dust cloud is just totally blocked out. But then if you switch to the infrared, where less light is absorbed, you can actually see through, and you can see the stars behind, and you can see that they look reddened. And actually, I think all of you are already familiar with this effect, kind of whether you know it or not, because this is happening, a similar process is happening in the Earth's atmosphere every day. So this is the same reason that the sky is blue. So when we have sunlight, it comes in through the Earth's atmosphere. Some of the blue light preferentially gets scattered around in the atmosphere. So you see these blue arrows, it gets bounced around in the atmosphere. And so now, if you look off in this direction, you see blue light coming toward you. And so now, if you look off some part of the sky, you see blue light coming toward you. That's the sky that looks blue. Whereas the redder light is able to pass through the atmosphere more easily. It's not scattered. And then again, at sunset, if you're, say, here on the top left of the Earth and looking at the sun, you're looking through kind of a small amount of atmosphere. But now, say we're sitting over here and the sun is setting on this side of the Earth. Now, the amount of atmosphere you have to look through is a lot longer. And so now the light has traveled much further. More of that blue light has been scattered out of your line of sight. It's been scattered away. And so now the sun looks red. Good. And so now we've kind of talked about dust in our own solar system. I'm going to talk a little bit about what I do, which is looking at dust in other galaxies. So as we've kind of already talked about before, in order to look through dust, it helps if we can look in the infrared, right? Because then we can see through the dust. But if we want to look at very far away galaxies, we need a big telescope and one that's very sensitive. And until recently, kind of infrared telescopes were being really outclassed by the Hubble Space Telescope, which is most sensitive to visible light. But now, just a couple years ago, the James Webb Space Telescope came online. And so this is an infrared telescope with a really giant gold-plated mirror that allows us to see the very most distant galaxies. And just to kind of, I know that maybe every astronomer you see on the news or whatever, they're always raving about the James Webb Telescope, how great it is and everything. But I want to give you just a kind of a comparison of what we had to work with before. So this is the previous infrared space telescope that we had. This is showing a patch of the sky where you can see there's a few bright stars. Maybe there's something kind of a little bit brighter in between these two stars. And then, I don't know, like over here, it's hard to tell if that's something real or maybe it's just kind of noise in the image. And then this is the same patch of sky with the James Webb Space Telescope. So you can see it's really a night and day difference between the sensitivity, right? You can see all these little faint things behind it now, and the spatial resolution. Now you can see structure and like the dense bright parts and the more diffuse parts in that part that we didn't even know if it was really there in the other image. And so it's really been a giant leap forward in a lot of fields of astronomy. And so now I want to show some of those same images of dust from the beginning of the talk. So on the left is what I showed at the beginning from the Hubble Space Telescope, and now on the right is the James Webb image. And so now you can see that all these spots where it's really dark in the visible light image, you can see all these stars embedded in the dust, even really bright ones here that are just totally obscured before. And so that's actually letting us peer right into these birth clouds where new stars are forming. And we're learning a lot about like how stars form. We're able to see the places where newborn stars are forming planets. It's really exciting. Just kind of another example showing more or less the same thing. And then the spatial resolution is really just mind-boggling. You can like blow these up, zoom way in, and the resolution doesn't seem to get worse, right? You can just keep on zooming in and see more and more detail. Okay, good. So now we have this awesome telescope. How do we use it to study other galaxies? Well, we talked about how astronomers like to use the entire electromagnetic spectrum, right? So not just visible light. And even this great infrared telescope is giving us just kind of one piece of the puzzle. So for example, here we have the Whirlpool galaxy, and we have pictures taken of it with different parts of the electromagnetic spectrum. So going all the way from the radio on the left to the infrared, visible light, ultraviolet, and even X-rays. And you can see that in the different images, different parts of the galaxy are bright. So for example, in the optical light, you're seeing mostly light from stars. The ultraviolet is mostly young stars. Infrared is showing the dust. And so if you can take a picture of a galaxy in all these different wavelengths, then you can gradually piece together all of the different components of the galaxy. You can try to understand everything that's happening within it by seeing all the different parts. And so then you have all these different parts. So you can make a plot of all of the energy that's coming from across the electromagnetic spectrum. So you have emission from the stars, from the dust. You can even split up emission from young and old stars and try and decode the entire history of this galaxy. Okay, so now we have kind of a picture of how one galaxy may have been built up, how it grew. Now we want to do it for loads of galaxies. So now we want to take an image and do that for every one of the galaxies, say, in this image. And then when we do that, we have lots of galaxies that we know how they grow. We can try to build a timeline of how galaxies grow over the history of the universe. And so that's kind of the general area of my research. So how do galaxies grow? When did they form their stars? And that's kind of the general question that we're trying to figure out. But some of those questions are really tied up into the properties of the dust that we've been talking about. So for example, if we want to know when galaxies formed their stars, we saw that if you just look with visible light, you can't see all the stars because of all the dust, right? So we need to be able to account for dust in order to know how many stars a galaxy has formed, how many stars have formed over the history of the universe. We want to know how galaxies in the early universe might have been different from galaxies today. So we know that over time the universe has expanded, the universe has cooled down. So we actually can see that through one way, the tracer being dust, looking at temperature of dust over time, that the universe is cooled over time as it expanded. And then finally, another question we can ask is all these metals that we've been talking about. So when did stars form these metals? So how quickly in the history of the universe are stars able to fuse these metals together and then spread them around, and that whole recycling process happen in order to have enough metal to form rocky planets like the Earth, where life might evolve. And so, yeah, so, and these questions especially I'm happy to talk more about, but otherwise, that's it. And I hope that you learned something. And I'll be happy to take any questions anyone has.
Okej, zdaj pa vprašanje lahko postavite direktno v angleščini, pa seveda slovenščini, da se prevedem.
I'm not sure if this is your area of expertise, but I heard there was some conundrum when James Webb Telescope started to bring back images about the actual age of the universe. I'm not sure if it got resolved or not.
Right, sure. So, right, so some of the early James Webb results, there were some surprises that have kind of forced us to kind of revisit our models of how the universe changed over time, right? So answering these questions that I'm talking about. So maybe, I don't know if it's exactly the one you're referring to, but one thing that the telescope found is that there's more very large galaxies in the very early universe, and galaxies that are so large and have so many stars that it would be actually hard to form that many in the short amount of time since the Big Bang in the era that they were found. And so over time, I think we've come to be able to account for them more. So I'm not aware of any of these kind of universe-breaking galaxies. And part of the reason is a kind of just more sophisticated analysis. Some of it is just obtaining more data and finding that maybe with a little bit of data, there's maybe two solutions to the same problem. And so you get more data and it rules out one of the solutions, right? But we're still working toward better understanding kind of these very early galaxies. Mm-hmm.
One, maybe two. Actually, when you were talking about the stars in the fusion model, you mentioned that we keep getting heavier elements as they fuse together. What's the physical law or property that stops it at some point? Like, why doesn't it go further, right? It stops, I guess, with iron or.
Right. So the energy that's required to fuse the atoms together becomes greater than the amount of energy that's kind of is produced in the center of the star, right? So the center of the star, there's the temperature of the star, the heat, kind of determines how fast the molecules can move, how much energy can be put into the collision of the atoms, and you need to overcome some barrier in energy in order to smash heavier elements together. And so the mass of the star determines how hot the center can get, and so that determines how heavy the elements it can form can be.
But as a consequence, are we kind of like running out of lighter elements? I mean.
No, so the universe is still roughly like 98% hydrogen. So there's no worries there.
So I mean, the hydrogen is being consumed. It's not.
Right, it's being consumed, but there's just so much vastly more of it that even in the entire 13 billion year history of the universe, all of that fusion has made a negligible impact on the amount of hydrogen in the universe.
Well, first of all, thank you for your thought. My question is regarding, I'm like biochemist, so this might be
Okay.
out there a bit, but you mentioned that there are a lot of kind of complex, organic, even aromatic molecules that you showed, right? So how do you determine their kind of identity? Like, do they have to be collected and analyzed? Because it's kind of trickier. We like elements could just check the spectra, right?
Yeah, so so a lot of the identification is able to be done because of lab work that's done on Earth, right? So you build, right, sorry, some of these aromatic molecules, right? And then you can measure where their atomic transitions are, right? What energies are associated. And then so we know that if there's light emitted at a very specific wavelength, then it's likely tied to this molecule. And so if we see light at that wavelength coming from space, we can infer that that molecule that we saw in the lab is out there. Yeah, exactly. It's like a fingerprint. Yep. Who collects them? Oh, who can access? Oh, it's public. Yeah. So through NASA. So if you go through their website, you'll find something that's called the Mikulski Archive for Space Telescopes. You should be able to, if you just kind of search for it, you should be able to find it. But that's where the whole repository is of all of the James Webb data that's been taken. So some of the very most recent data, the scientists that organize the observations are allowed to keep it private for a short amount of time, but it does eventually all become public. Right, so kind of talking more about this process here. Right, so it does take kind of a lot of time. So it takes kind of millions of years for these clouds to condense. So you can imagine that for anything in the universe, if you have gravity wants to pull it together, right? And so, but when you have things that are hot, they like to bounce around and stay far apart, right? So, for example, in these gas clouds, you need to somehow cool them down enough so that gravity can overcome their temperature, right? And so that's what I was trying to talk about, how the dust and the metals help in that process of cooling the gas down. Is that kind of related? Does that answer your question?
Če lahko prevedete, lahko se ne to. Govoril gospod, ko ta prah postane asteroide, se oblikuje potem do Zemlje. Ko pa pride do te energije, ki v središču Zemlje, torej te visoke temperature posega prahu.
So he's asking, yeah, so you were talking about how dust is forming in the earth, so he's asking how the temperature is rising to the core of the earth, basically.
Okay, so
Why so?
right, so right, so as these dust particles come together and form like these larger and larger pieces, eventually up to the size of a planet, right? The gravitational force holding it together gets to be very, very strong when you get to something the size of the planet. And so since it's being pushed together so hard, if you try to squish a rock, right, it doesn't seem like it couldn't go anywhere, right? Well, the gravity is so strong, it actually does squish the rock down, but as it does, the inside of it heats up. And so that's kind of what's heating the center of the Earth. And there's also other processes going on as well. So there's some of the heavier elements that are radioactive, so elements that just spontaneously give off radiation, are also heating the interior of the Earth as well. Yep.
The galaxy is just this, but on a much larger scale. I mean, in the process, the same. So just the stars are being formed.
So I guess it's analogous. Yeah. So whenever you have gas flowing, whether it's kind of getting funneled down into a molecular cloud where stars form, or you have gas from kind of the flowing into a galaxy, that gas has angular momentum, right? And so I think maybe most people here have heard that momentum has to be conserved, right? So it's not just like linear momentum where if I smash one thing into another, the other thing has to move. It also happens with spinning energy too. And so as the gas flows in, it has some amount of spin, and as it's getting concentrated into a smaller area, it looks like it's spinning more. And it's the same physics that causes the gas in a galaxy, the disks, to kind of flatten and spin as in a planetary disk.
I have a question. You showed how the molecules of the metal are in relationship with the dust. I think it was
At the beginning.
Is this something that we believe it's happening, or is it something that we prove and are doing it on an experiment?
Right. So these, this is actually related to the question we had before. So where the amount of energy that's released from these this either behavior in the molecules or from the atomic transitions when electrons are moving around in an atom, that provides actually like a very unique fingerprint is a good analogy for it, that these are very specific energies. And so when we see light that has that exact amount of energy, we can be confident that we are seeing specifically that like atom or molecule. We can, so so all of what I've been showing today are astronomical images, right? So where we see kind of light over a broad range, you'd have to look at what we would call a spectrum, where you can see the amount of light, maybe if I go to kind of go to here, right? So where we have like this plot of how much energy is being emitted as a function of the wavelength, right? But you can get very, very sensitive measurements of this over short ranges. So where you know exactly how much energy is emitted over a very small range. And so that in that range is fine enough where we can identify like kind of these fingerprints of individual molecules and atoms.
In joules, or what is the energy or
Flux density. So, so an energy, or an energy over an area per unit frequency.
Freedom units. Okay, če ne, se lahko zahvalim Niku. Kot je tradicionalno, vsak drugi četrtek večeri na observatoriju je takrat seveda stavilo.
Tako da več sreče naslednji mesec, ki imamo še eno predavanje, če ne pa je še dan odprtih vrat, 20. marec. Probate pridružiti, vem, da karte hitro poidejo. Ja. Hvala za obisk, pa upam, da se vidimo naslednji mesec. Dio.